Howdy, amateur astronauts. I hope you're enjoying our conversations on the awesomeness of space exploration. But you might not know that Are We There Yet is supported by listeners just like you. So consider showing your support with a financial contribution to WMFE. You can do that by visiting wmfe.org/support. Your gift helps us better explore exploration. And thanks. From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast that asks the question, are we there yet? Hi, I'm Brendan Byrne. NASA wants to head to Mars. And to do that, they're developing a brand new rocket called the Space Launch System, or SLS. It's a rocket, but it's borrowing some parts from the Space Shuttle. The main engines on SLS, for example, are the RS-25 engines used on Shuttle. But just leaving the Earth's gravity requires a huge amount of thrust. So the hammer that's going to launch SLS are two solid rocket boosters. Now the Shuttle used these technologies too. They provide a lot of thrust really, really fast. Engineers at NASA just wrapped up a test firing of the boosters' engines out in Utah. Bruce Tiller is the deputy manager for SLS boosters at NASA. He was at the test and he joins us to talk all things solid rocket boosters. Bruce, thanks for speaking with me.
I'm glad to be here, Brendan.
So, Bruce, take me back to that booster test that happened out in Utah. What were you testing, and what were you looking for?
Sure. Yeah, no, this was a big milestone for us. It was called QM2, which stands for Qualification Motor Number 2. So, for our booster, which I'll describe to you, it's one of the major elements of the Space Launch System. This was our last qualification ground test to qualify the performance of that motor. And actually, we did this one at 40 degrees. So we actually cooled this motor down to 40 degrees F. The previous qualification test, we had done at 90 degrees F. So that gives us the range that we expect to see on launch day when we plan to launch this SLS rocket from Kennedy Space Center.
And so what did you do for the actual test? You fired this thing full thrust, right?
Yeah, so what we do, you know, you'd love to fire one vertically because that's the way it will fly, but that's not really feasible. So we actually lay this 155-foot booster on its side. It's actually the motor, not the booster, but the motor part on its side. And then we have it contained with a heavy metal structure and a lot of concrete to keep it from going anywhere. And then I guess we practiced lots of dry runs for many times up in the month preceding the test. And then finally on test day, I guess we had a few thousand, 5,000 to 10,000 people there to watch it because it's a very spectacular sight. But then we light the motor, ignite the motor, we call it. And it fires for 2 minutes horizontally into the mountainside. And it's a spectacular cloud that goes very high in the sky. You could imagine this motor burns 5.5 tons of propellant per second. So that generates quite a display. And so that was our test. And it went very, very well. We're looking at the data now. It all looks good. In a qualification test, you really don't expect to get surprises. We really didn't want to learn much in this test. What we want to do is confirm what we already know, and that's what we're doing. And it'll take us quite a while to not only look at all the test data we measured, but also to disassemble the motor and inspect all the parts and understand how the hardware behaved as well. But we've just gotten started on that, but everything we've looked at from the test data so far looks great. Looks very, very good.
How much thrust does that thing put out?
It puts out a lot. Each motor puts out, let me describe it this way. The peak thrust that you can get out of a motor is 3.6 million pounds of thrust. That's a big number. Now, it actually has a profile during the motor firing. You know, over that 2 minutes that we burn, it actually goes up and down, and that's by design. We designed the motor to behave that way, and we did that under Shuttle as well. You know, this is leveraged off of a lot of Shuttle technology. In fact, the motor cases on this test, when I talk about the metal cases in which the propellant is cast, those cases flew 40 times on Shuttle. But yes, it's a lot of thrust. So the two motors, when you assemble them into boosters, and you have to add some parts to that, you've got to add the aft structures and the forward structures. And there's one on either side of this SLS rocket. If you remember the shuttle configuration, we had 4-segment boosters on either side of the shuttle, either side of the external tank. This is the same, except they're 5-segment boosters, and they'll be on either side of what we're calling the core stage for SLS. At any rate, those 2 boosters will provide 75% of the thrust required for liftoff. And that's really why you have solid rocket motors. They're very high thrust propulsion systems. And so when you got to get off the ground, that's what you need. You need a lot of high thrust early in your mission, and that's what these boosters provide.
Bruce, how does a solid rocket booster differ from something like a liquid engine?
That's a good question. A solid rocket booster actually contains all the propellant in a solid form, solidified in the case. If you think of a liquid booster, what you think of is 2 tanks and a liquid rocket engine at the bottom, and it has a lot of valves and it has a lot of controls, and normally those are for example, the engines that are on the SLS, those are RS-25s, and they burn oxygen and hydrogen. So in those tanks, we'll put liquid oxygen and liquid hydrogen. That's cryogenic fluid. It's very, very cold. It requires you to tank the vehicle over a certain number of hours to get ready. The advantage of that, of course, is you even though it takes you a long time to get ready to launch, you can actually turn on the engines, the liquid engines, and turn them off if they're not running correctly. A solid is different in that you build in that oxidizer and that fuel into the cases when you actually, what we call, cast the propellant. You take one of these segments, segment by segment, we'll have a metal case. If you can imagine lowering this big metal case down into a deep pit, and in that pit you've actually mixed up this propellant in a special remote mixing building, and once it's mixed, they bring it by truck over to the casting pits, and they actually have a special vacuum bell they put on it, and then they'll drop that bucket of propellant essentially down into the pit. And you'll do about 40 of those per segment. I think it takes close to a full day of continuous mixing and casting to put that together. But then you heat that thing and you cure that propellant into the shape you want, and that's why it's called casting. And you cast it in the shape you want, and you heat it, it cures, it becomes like a solid rubber material. It's pretty safe to handle at that point, and you can actually store them. Our boosters are good for 8 years. So you can then build those segments separately, and then because the whole booster is too large to actually transport in one piece, and it's actually too large to manufacture in one piece, we'll take each segment and put them on a train car, and we'll transport them from Utah, which is where they're manufactured by our manufacturer, who's Orbital ATK, and they'll actually ship them on a train from there all the way down to KSC in separate cars, at which point we will stack them in the VAB, in the Vehicle Assembly Building, there at KSC. And so the difference between a solid, in general terms, a solid is used when you need very high thrust applications, because it's usually higher thrust than a liquid rocket engine. Though it's a little less efficient, it's higher thrust. And so when you need it's sort of the heavy hammer if you're trying to get off the ground, so to speak.
Now, how do you ignite these things?
So we ignite them with what we call an ignition train. And it starts with an electrical signal, which then goes to what's called a standard initiator, which turns that electrical signal into a small spark. That spark ignites some small chemicals. I believe the first part of the train is maybe some boron pellets. I don't quote me on that, but there are some chemicals that go from small to large. That's what I'm trying to say. So you'll ignite a small basket of things, which eventually light what we call an initiator, an igniter, which is kind of a small solid rocket motor that is bolted to the top of our motor. It's in the forward dome of the motor. And that small motor, it has holes in it, so when the flame comes out of it, it comes out of these holes. That flame will travel all the way down the 100 feet of the motor, and then it will ignite the middle of the motor to light the main motor. The part I probably forgot to mention, if you imagine one of these motors has essentially a hole all the way down the middle. So we cast this solid propellant around what we call a core structure, and then we remove that core. So what's left is a motor that's got propellant from the walls, the metal cases that I described to you, all the way out to a hole in the middle. And so you light it from the inside. That's how you get it burning. And then when it burns, it's burning from that inside surface back to the metal wall. And that's what burns out in those 2 minutes is, and when we talk about burn rates, we talk about inches per second. How far does it burn from that hot gas surface back to the metal wall?
And is that kind of how you control the thrust profile that you were talking about earlier?
It certainly is. We shape that grain, and all motors and missiles have different requirements for the kind of burn profile they want. In other words, how do they want their thrust to vary over time? Ours was essentially designed during the shuttle days, and so we have what we call fins. There's a unique shape up in the front end of the booster, but all the other 4 segments from the front to the back, they pretty much just have a hole down the middle. But you design that shape to get the burn profile you want and to get the thrust shape during the mission that you want. You want it to drop a little bit, just like we throttle the engines during flight. You reach a max dynamic pressure during flight, and you want everything to throttle down a little bit to relieve the structural loads on the vehicle. And so our boosters have that built in as well.
Can't just gun it pedal to the metal, right?
That's exactly right. You can't just gun it. And then not only the structures, the astronauts probably wouldn't like that either if we were to just gun it. So there are G limitations on the crew as well, as there should be.
Speaking of astronauts, you mentioned that once you light these things, there's no turning them off. Is there an issue of safety that you have to think about when you're planning a mission profile or something like that when you do have humans on board?
Absolutely. But we qualify these things for flight, manned or unmanned. To us, the booster is qualified. It's qualified, and so we consider them qualified for flight even on EM1 because we're going through all the same procedures we would go through even if it were the first flight was manned. So for us, it makes no difference. But absolutely, safety is a primary concern for us, and the way you control that really in a solid is through process control. That's one of the main features you do. Along with qualification, it's a lot of process control. You make sure you build it. First, you make sure the design works, and we do that through this development testing and then the certification testing to make sure all our joints are safe, all our structures are held up, that it behaves just like that's why we disassemble them after the static test. We look at all the internal parts and make sure that nothing leaked. I guess it's kind of a short way to say it, but nothing broke and nothing leaked. And once you've proven that to yourself, then you really lock down the manufacturing processes so that every time you build one, you want it to be exactly the same as the last one. And that's probably the way we most capture the safety part of it, because as you say, once you light it, it's going to burn. But if you have controlled the build like you wanted to, then it'll burn just like the last one did. The other thing that the SLS vehicle has on it is an abort system, which I think it was a key safety requirement when we developed this vehicle after the shuttle program, because the shuttle did not have one, a good abort capability for the astronauts. This one does. It goes back to the design we had during Saturn. And so on the very top of Orion, the crew capsule is called Orion, and it's sitting at the top of this rocket. It has on top of it another solid rocket motor, actually, that's like a little tower. You'll see it in the pictures right on top of the Orion. Should something go wrong, either with the motors or the core stage or anything below, if something goes wrong with the rocket, a couple of things could happen. first, we have software to watch for that, and when the computer decides there's a problem, then and the astronauts are able to abort, this motor on the top of the rocket will pull them to safety. It's extremely fast burning, high thrust. I think they pull maybe 15 Gs in this thing if they have to use it. It would not be a pleasant ride, but it would pull them away from a damaged rocket, and it has some vehicle controls as well. So then their parachutes would work and they would land safely in the water. So that's a new system we designed with obviously the crew safety in mind.
And to your point, that's the solid rocket booster when you need a lot of thrust and you need it really fast. So that's why you guys put that on top, right?
Yes. You don't have time in an emergency. You don't have time to fuel up a liquid system. You've got to have a solid that will ignite immediately and pull you to safety. And that's what that one does.
Bruce Tiller, the next big test for these boosters is going to be EM1. Are you ready for that? And how excited are you for that?
We are really excited about EM1, and no, we're not ready. I'll just say that. The motor is one part of the entire booster that we're building. SLS in overall has made it past its critical design review. All of the elements are off into manufacturing now. We are actually, if we just look at our motors, we've cast 3 segments of the EM1 motors, so we're well on our way to making the motors for EM1. But there's other parts too. I think I described what we call the booster includes some forward and aft structures, and we're actually building those, assembling those down at KSC. Just as we did during shuttle days, we have a facility on site there at Kennedy Space Center where we, as in shuttle, we assemble the aft assembly, which includes our thrust vector control system. We assemble the forward assembly, which has the frustum and the nose cap up there, and it has all our new avionics boxes in it. And it used to have parachutes in it. We don't have parachutes in this booster, but that is all assembled at KSC. We deliver those to the Ground Systems Development Organization. They actually assemble. They have a place called the RPSF, and I'm sorry I don't remember that acronym. But that's where they will assemble that first part of the booster. The very first part that goes on the mobile launcher, the first part of this that actually touches the mobile launcher is the booster, the aft assembly. And that's from there you build the rocket. In other words, you start with that aft assembly. It, just as in shuttle days, it sits on the mobile launcher, and then you stack the boosters, one segment after the other. Then you put the forward assembly on the top. And once you've done both boosters, then you can bring in the core stage and lower it down in between. And it actually rests on the boosters themselves. The boosters support the entire rocket. So yes, that's the procedure we'll go through to get ready for EM1. And so we are in the middle of manufacturing those aft and forward assemblies down at KSC. But we really just started those. This year is we're after QM2, we're really turning our focus down to Florida now. And we're really going to focus on getting those forward and aft assemblies together. That's a complicated assembly. It's got a lot of electronics in it as well as some major structures. And so that's a big focus for us now that we've gotten through this successful QM2 test.
Bruce, as you say, these boosters, these motors, they are the foundation of the SLS. You build your SLS around it, but it's also the foundation of our efforts to get humans to Mars. What is it like working on the technology that is so critical to that mission?
Well, I'll tell you, it's very exciting. It's every once in a while, we all talk about this. You have to look up every once in a while. We're very busy. We're working on our little piece of the puzzle, right? So our little boosters, and we're working on our part of it. But every once in a while, you have to look up and go, what am I a part of? Why am I doing this? And that's where you get to things like the mission to Mars, and you get to things like exploration, deep space exploration. That doesn't even include just the manned missions. We've got some big unmanned missions planned as well, and that's really exciting. I don't pretend to understand what all the space scientists need from all that, but those guys, they have to get into space, and that's our job as engineers, is to get them where they need to go. And so right now we're focused on our little piece of it, but absolutely it's exciting to think about when that thing goes up, or we get some more great Hubble pictures or robot pictures from Mars, or that we could be we can be a part of that is pretty exciting. I'm really looking forward to it. The whole team is. It's going to be I think it'll be exciting for the country too. I think when we get that vehicle stood up and it starts rolling out of the VAB at KSC, it's going to be extremely dramatic. I think we'll get a lot of public interest. Everywhere we talk about this, everyone's pretty excited. And even though Mars is quite a ways away, EM1 is not. It's actually amazingly close. So we're working hard to try to meet those schedules and really are looking forward to that first launch.
I've been speaking with Bruce Tiller. He's the NASA Deputy Manager for SLS Boosters. Bruce, thanks so much for chatting with me.
Absolutely. Good talking to you.
Well, that's about it for this episode. Support for Are We There Yet comes from the listeners of WMFE. You can follow the show online or on Twitter at AWTYMars. Are We There Yet, Mars? Or reach out to me in the Twitterverse. I'm at Space Brendan. Leave us a review on iTunes. That's how more people learn about this podcast. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. For more space news online, visit us at WMFE.org/space. I'm Brendan Byrne. Thanks for listening.